now we can start next session. This is the first session of contributed talks. The contributed talks were selected by a scientific committee based on the abstracts of Poster's presentation that you sent. So it was upgrade from Poster. And the first presenter is Rafał Mirek. Rafał, right? Yes. From our university, from the University of Warsaw, from the Faculty of Physics. And he will tell about neuromorphic neural networks. Please, stage is yours.
Thank you for the introduction. Yes, I'm a PhD student in the Polariton group, which is at the Faculty of Physics on the University of Warsaw. And we are dreaming on building a neural network which will be fully optical. And this is our dream. And I'm an experimentalist, so I will show you two experiments, which I hope will convince you that we are quite close to reach this goal. So we are working on polaritons, and you can imagine them as quasi-particles, which are mixed light matter particles. And so you have two states, matter state and light state, and they mix with each other, and they create two new states, with one with the lower energy and another one with higher energy. And these are the polaritons. And what we do usually is confining photons in a special structure which is called microcavity, and we confine excitons in a structure which is called quantum well. And these two types of states are strongly interacting with each other. They couple to each other strongly, and they form lower polariton and upper polariton. And how do we do it in practice? Let's imagine a structure which is made of different layers of different materials with different refractive indices and different thickness. And for such a structure, we can obtain such a relation of reflectivity versus wavelength. So there is some area where the reflectivity is very close to 1, even equal 1. So that means that the photon which has a wavelength in this range will completely reflect from the structure. So we will have full reflection. If we put a defect in such a structure in the form of a different layer with different thickness, but very special thickness, which is very close to the lambda b, then we can form a mode in such a relation. So we'll have a very specific wavelength for which the photon will go into this sample. So this is the way how we can confine the photons in a structure. And this is the semiconductor structure. If we put a quantum well inside this microcavity, so this structure where we confine a photon, we could also confine an exciton. So what we usually do, we also grow a quantum well inside the structure, and here we will have an excitons which will be confined in one direction. And the typical Hamiltonian, which is describing this system, is formed. So it has energy of the exciton, energy of photon, and the coupling strength, which is given by the omega. And the typical experiment that we see is we shine the laser light on the sample, and we observe the emission on the CCD camera. So with increasing power of the excitation laser, we increase the increasing signal. It's quite easy. So this is very easy experiment. And if we plot the photoluminescence, so the emission in a function of the energy of the pulses which are going to the sample, you can see a clear nonlinearities. And there is some threshold which is called condensation threshold. These particles which I'm talking about are bosonic, so they can undergo a phase transition to the Bose-Einstein condensate. And this is what you see in here. So above some threshold, we have phase transition to the condensate, which is indicated by the nonlinear increase of the intensity. We have also another indications, but this is the easiest one to see. So the typical experiment that we make is using input pulses, which are creating the exciton-polariton condensate, and we measure the nonlinear output on the CCD camera. So it's really simple. And the most important thing that I want to say is that the properties of exciton-polaritons are adopted from the matter and light component. Yes.
So how to understand that a stronger pulse actually causes condensation? Because you would kind of very naively expect that this brings more energy into the system, so it would heat up the system.
Yes, so yes, we are heating in some sense the system, but the most important thing is that when you increase the excitation power, so energy of the pulse, you create more and more particles in the small volume. So they are there is more and more of them. So the overlap between the wave function is increasing, the wave function of the particles. So then they start to fill each other with increasing excitation power because there is more and more of them, and they let's say they undergo this phase transition due to this overlapping of the wave function, which is increasing with increasing excitation power. So this is how it goes. Okay. So the most important thing is that we really have properties of exciton-polaritons adopted from photonic and matter components. So we have very low effective mass, which is 10 to minus 5 of mass of electron. So this is really low, and this allows for phase transition at room temperature. So we can really observe Bose-Einstein condensation at room temperature for these particles. They have very short lifetime, below 100 picoseconds. So this allows for very fast computation for very, very fast operation. We have also Polariton-Polariton interactions due to this excitonic component. So this will give us the large nonlinearities and also nonlinear phase transition to condensate, which is also giving us the large nonlinearities which we saw on the previous slide. So this is a really great system to mimic some neural networks or to make some nonlinear media. So let's go to the problem that we want to solve today. We know from the lecture of Roman 2 days ago, he said that there are some linearly separable problems. So if we have two classes and we can separate these classes with the linear function, this is the linearly separable problem. But there are also non-linearly separable problems, and they are not separable with the linear function. And the logic gates are examples of the classification problems. So for example, AND gate is linearly separable problem, but the XOR gate is not linearly separable problem. And we will focus today mostly on XOR gate. So what we will do, what people usually do, is using nonlinear function to classify these two classes, or they can nonlinearly transform the system to higher dimensionality, and then they can use linear function to separate these two classes. So we will use nonlinearities present in our system to nonlinearly transform the data, and then we will perform linear classification. So the scheme of the experiment will be very similar to what I shown before. So we will have input sequence of some, so we will have some pulses with smaller and larger power, which will encode 0 and 1, logic 0 and logic 1. They will create exciton-polariton condensates, and then we will perform linear classification on this nonlinear response. And then we will get the nonlinear output. So this is the first scheme of the experiment. We have two pulses, two beams of pulses, which are separated in space. And these two beams of pulses will go on the sample on the same at the same time, and we will measure the nonlinear output. So this is the result that we had. So these are the 4 states that we wanted to encode, and this is the emission from 2 condensates on the CCD camera. So we encode 00, 01, 10, 11 by the excitation power of these pulses. So the first bit is encoded by the 1.2 picojoule or 2.6 picojoules, and the second beam 5.2 or 10.5. So we just change the excitation power of the pulses or the energy of the pulses, and this is how we encode the states. And these are the results of the emission from the condensate, which I marked with the red circle. So we can observe here huge nonlinearities, but also we observe some noise. So to compare these nonlinearities with the noise, we define the degree of nonlinearities, which is the sum of mean values of intensity at state 0, 0, and 1, 1, minus 0, 1, minus 1, 0. And this is divided by the variance. So we can define the degree of nonlinearities for the first condensate and the second condensate, and we have different nonlinearities. For the first one, it was 9. For the second one, it was 13. And what we did was linear classification, which was done later. So we produced the samples for testing and for training. It was a lot of them, like hundreds of thousands. And we performed XOR gates, and then we tested if the operations are really making this XOR operation. And we did it for many different systems with many different degrees of nonlinearities. And what we saw that when we are above degree of nonlinearities above 5, then we obtain 100% accuracy rate in constructing XOR gate. So we went farther with this, and we tried to construct a neural network, which was binarized neural network, working on these XOR gates. So what we did was binarizing the MNIST digits from the MNIST data set, and we randomly chosen the pairs of pixels on this pictures, and these pairs of pixels were the inputs of the XOR gates in the hidden layer. And then we performed the linear classification on this part, and we got the result. And what we saw, the accuracy rate of classification of the MNIST data digits, handwritten digits, was depending on the number of gates in this hidden layer, and we could reach above 96%. Yes.
This randomly chosen pixels were the same for all pictures?
Yes,
or? Okay.
That's a great question. So we randomly chosen this pairs of pixels, but for each picture, the same pair of pixels was going to the same gate. So that was quite important in this case. Yes. So we got 96% of accuracy rate, which is now the leading accuracy rate in such implementations. But I need to say that this is optoelectronic system. So we are using the data which we collected in the optical system, but then we use them in the computer to perform the computation. But all we did in here was linear classification. So the nonlinearities were coming only from our system. So I would like to make this clear. So the second experiment will be performing an all-optical XOR gate. So we want to make an all-optical system, and for this purpose we used two beams which were focused on the same position on the sample, and these were different pulses with different excitation powers. They were focused on the same spots, on the samples. They were creating the same condensate, and we were measuring the emission the same as before. And that was the experimental setup. I know that it can look complex, for now, but I will try to explain it in the details. So that was the first beam of the laser. So we go this way and we excite the sample, which is in here in the cryostat at 4 Kelvin in the liquid helium temperature. So this is the first beam of the laser. And that was the second beam of the laser. So we have pulses which are going this way and that way. Then we collect the emission from the sample, which is going to the CCD camera. And I already marked the outputs in here. So we were trying to build this setup to solve this set of equations. That was the main idea of this. And in this set of equations, the output from the sample will be these 4 components. So output for state 1, 1, 1, 0, 0, 1, and 0, 0. I hope this is clear for now. Then we have also these components. So this is the intensity coming from the laser, from the first beam. So this first beam was exciting the sample, but it also goes on the beam splitter, and then it's directed on the CCD camera, so on the same spot on the CCD camera as the output. We also put the second beam, which was exciting the sample this way. We put this also on the CCD camera. So we have the intensity of the second laser pulses on the CCD camera. So we can also get these components. So the last thing that we need to get is these weights, W1, W2, W3. And we want to have these states 1, 1 and 0, 0 the same, and 1, 0 and 0, 1 also the same, but different from the states before. So what we did was measuring the intensity of the pulses for high power and for low power. Then we measured the second beam for high power and low power. We measured the output for these two pulses exciting the sample. So we observed the emission from the condensate when we have two laser pulses with low power and so on. And based on this, we could calculate these weights. So that was our task based on these measurements. And we could realize these weights. I will go back to the experimental setup, W1, W2, and W3 using optical filters. So these were just the optical filters which were giving us smaller power in the transmission. So we calculated these weights, and using these weights on the optical table, we could run the experiment again, but this time mixing all these intensities. So on intensity of the first beam, second beam, and the output, and we got this result. So we have two distinct states. This is the lower state, the same here, and higher state, which is here. And the nonlinear degree of nonlinearities for this were about 8. So I would say it's quite good. So, and this is fully optical system. So we don't need to do anything with this data. It's just performing calculations. And due to the photonic properties of exciton-polaritons, we only need a power of less than 16 picojoules. That's the first thing. And the time that we need to perform this calculation is below the 500 picoseconds. But this is really overestimating because we can really clearly see that it's even less. So yeah, to summarize, I showed you the optoelectronic realization of the XOR gate, the neural network, which was also optoelectronic, but also I showed you the XOR gate, which was all optical, fully all optical system, and all of that was done on exciton-polaritons, and more details is given in this publication. So I encourage you to check it. Thank you.
Thank you very much for this nice talk showing that like physical realization of neural network are coming. Okay, so now we have almost 10 minutes for questions, so lots of time, please.
Okay, thank you. That was a really great talk. Thank you very much.
Thank you.
I have not yet really understood like how you are training these weights. Could you maybe explain that again briefly?
Yes. So I'm not training them. I can calculate them very specifically. So if I have these results, I can just calculate the mean value of these intensities and just put them in the equation. So what I have here is only W1, W2, and W3 to estimate or to calculate, but I have 4 equations. So A and B can be really anything. I want A and B to be as high as I want, and I know that the output is the less intense than the laser. So I always put W3 equal to 1, and then W1, W2 are very small, and I can do it in such a way that A and B will be as high as as possible. So I can always go with W1, W2, and W3 from 0 to 1 because this is just an optical filter. So it's quite easy to solve them. I'm not sure if I.
Yes, yeah, this is definitely helpful. It's still like hard for me to comprehend again then like where these measurements come from, but
I know these values. So the red one, orange one, and blue one. And I solved these equations with the knowledge of these values, which I measured before. So the training process is just measuring laser alone, the second laser alone on the CCD camera, and the output alone, like without any other things. And then at the end, I mix them together with these weights, and that's all.
Ah, yeah, okay, all right. Thank you very much.
This may be a naive question, but what do you need the sorry, I'm not sure what the name is, excitons for? Because if you naively build this with 2 lasers of different intensity, you can also kind of get an XOR logic.
Yes, I agree. So I think the main thing is these interactions. So everything what I show today can be done in the fully photonic system without an excitonic component. This I agree. So we could use, for example, some interference effects or something like that. So this is the I would say this is the scheme which you can use in any nonlinear system, and any photonic system will be also perfect. But if you want to scale this up, then it's quite hard because you really need nonlinearities when you want to, for example, connect these gates in the further realizations of the networks. So for construction of single XOR gate, that would be enough to use the photonic system, and that's all. So I can use just 2 lasers and that's all. But then if you want to scale up, you really need these interactions, and this is why I think that's why the photonic computers are not working right now.
Okay, but can you specify what exactly is the interaction doing to help you scale up?
So it helps to connect these nodes between each other. So for example, if you want to have 2 different nodes which will speak with each other, so somehow connect them, then you really need to have some interactions.
Yeah, okay. Yeah, thanks. Great.
Okay, this one question was solved already.
Sorry, but I think I still don't understand the training process, how this relates to data in the end. I mean, like obviously I understand what you measure and stuff, but like how does this relate to data and training the in the end the network to to do the task it has to do? I mean, obviously it's a theorist versus experimentalist misunderstanding probably, but
so we are training the data by measuring the laser pulse on the CCD camera to check the intensity of this laser pulse, and that's the beginning. Then we measure the second laser on the CCD camera to see the response of the CCD camera when we shine the light on it, and then we also measure the intensity coming from the sample. So this is the intensity which is giving us the nonlinearities. And to use them, we need to connect the output with the intensities of the laser, which are weighted in some way. And this learning this process is only to learn what are the weights. So how much laser I need to add to this data to get two distinct states, which are the lower and higher state. So I also need a very specific states, which I could use for the next XOR gate if I wanted to put it as an input to another. So the main problem is how to add this laser to the output to get two separate states which have different intensities.
Right. I think I still don't understand how this corresponds to the learning process, but that's fine. We can discuss also later.
Yeah.
Sorry, but this is a very short and probably even more the most naive question. So do I understand correctly that you use your optoelectronic device only to simulate, to construct the XOR gates, but then the second part, the linear classifier is just a classical algorithm on a computer. Is that correct?
Yes, I partially agree. So the linear classifications, the linear classification was done completely on the computer, and what was done on the setup was only measuring these nonlinearities, so collecting data which is nonlinear. So we got the nonlinear data, we had these nonlinearities, and then we didn't need to perform any nonlinear operations. We just performed linear classification on this. So the nonlinearities were large enough to perform the linear classification, and that's what was done on the computer.
Maybe in regards to the two questions before, I think the confusion is from the terminology. What you're doing is not really training a neural network to perform a data-specific task. You're trying to calibrate your system to perform
I also
XOR.
wouldn't call it the training. Yes,
yeah.
And if I did it, I'm sorry, because what we've done was just let's say measuring data to get these weights, but we were not training anything at all. So I wouldn't call it training, yes, because we were not adjusting any weights. We just get them from the data.
Thanks for the very interesting talk. I thought that was nice results. Could you give any criteria of comparison, like in terms of accuracy of the classification? At the end, you also mentioned energy consumption and time. So yes. I suppose it's much faster than any computation on the computer and less energy consuming. And for the accuracy?
Yes, so let's start from the accuracy. So we could compare the accuracies for the handwritten digits classification, and we were comparing them with the standard procedure. So we were using the standard procedure for binarized digits and for not binarized digits, and it was much better. So I think the accuracies were there about 92 and 94%, but this is quite easy to check. And regarding the efficiency, I have a slide about it, but I need to find it. So it's somewhere here, I think. Let's see. Yes, so this is the slide that this is the slide from the presentation, which was from the paper, which was published 3 days ago, and this is the experiment that I showed you today. So we are somewhere here. So on this axis we have energy efficiency, and this is performance density. So we can also check how many operations per millimeter square per second we can do. So we are somewhere here, and we can still improve. So this is the very realistic case where we just change the excitation, because now we are exciting with very high energy. I didn't mention this, but we can also excite resonantly in this condensate. So with the energy of the condensate, and then we are really losing. We are not losing so much energy as in this case. So it's quite easy to go to this point, and this is our goal for now. And this is an ideal case. So this is the best what we can do with this system. So it would be really hard to get here, but this is really realistic. So we are somewhere here, and these are the standard realizations that are like the state-of-the-art realizations done in the world. So I think we are quite. We have a quite good result for now.
Just to compare it to like a normal computer computing, do you have any idea? Just
this would be really hard to compare, I think,
yeah,
because it's quite different system. So I don't want to do that. It would be really hard, I think. So yeah, you really need to know that we are talking about something very specific. This will be solving very specific tasks, and it's really hard to compare to a standard computer. I would say it would be really challenging to find a good measure of it, like to find a way to compare both of these systems.
Okay.
So we have just one last short comment or question. And
yes, but at the same time, let's maybe start changing the computers. So like.
Just a question of curiosity. So would it be possible at some point to integrate this into some really small circuit or really small devices, which would
Yes, it's really scalable. So all the optical systems are quite easy to scale down with the size. So let's see on the cameras in our phones, for example, you have a lot of lenses there and all this stuff. So I think it's quite easy. It's just, the first realization of such a system. So we really didn't care about even the energy efficiency and how fast it will work. So there is still a huge room for improvement, and yeah, we are on the good way for it. Yeah.
So unfortunately, more discussions. We have to move to the breaks and poster session. Once more, thanks for the speaker.
Thank you.
And